In the previous lab, we followed an example for a SN2 type reaction. In today's lab, we're going to look at another important reaction used in organic chemistry, which is called the Diels-Alder reaction. This is a very commonly used reaction in organic synthesis, and this reaction was discovered by Otto Diels and Kurt Alder, the scientist, and the reaction is named after them, and they received the Nobel Prize in Chemistry in 1950 for their discovery of this particular reaction. Basically, this is a chemical reaction between a conjugated diene, which is a molecule that contains at least two alkene groups, so it's very electron rich and has more resonance structures, so it's very stable, and it's reacted against another molecule that we call as a dienophile, and the special thing about the dienophile is it also has an alkyl group, but it's close by to an electron withdrawing group. So due to being in the proximity of the electron withdrawing group, this double bond is slightly lacking electrons because the electrons are pulled more towards the electron withdrawing group. That makes this double bond more susceptible to undertake a nucleophilic attack from an electron-rich compound. So that is what happens when we mix a diene and a dienophile together. This double bond will attack one of these carbons in order to eliminate the lack of electrons around this double bond, which causes electrons to shift this way and shift this way, and this double bond shift here. So once that electron shifting is completed, we're going to end up with a new molecule, and that new covalent bonds are going to be formed between the carbon here and the carbon here, and this carbon. So instead of four pi bonds that existed previously, we get rid of two of them and replace them with two sigma bonds, and we're able to get this more complex cyclic compound. As an example for a Diels-Alder reaction, we are following the chemical reaction between 1,3-butadiene. So it's a diene. You can see there are two alkene groups reacting with a dienophile, malic anhydride. So here's the alkene group in the dienophile, and it's in close proximity to two electron withdrawing groups. Oxygen, we know it's very electronegative, so oxygen is going to pull away the electrons it's sharing with the alkene group. That makes this double bond susceptible to a nucleophilic attack, so that allows an electron flow, allowing for two new sigma bonds to form between carbon atoms, and we end up with this very complex cyclic compound. And these two bonds are the new bonds, and you can see how the two reactants are connected together, and You can actually get questions of this type in the exam where you are given a die-in and a dienophile and asked to choose the correct product. So it's always going to be this one of these double bonds will attack the alkene group in the dienophile. That will cause the electrons to shift, and that alkene will no longer be present in the final product. Instead, it's going to form a new bond with the carbon of the other alkene in the diene, and that causes this double bond to shift to the next position. And now you can see in the final molecule, here's the two new bonds, and the double bond that used to be here is now shifted here, and the double bond that existed here is gone, and the double bond that existed here is also gone. So this is basically our reaction, and we are able to measure malic anhydride because it's a chemical that is available as a solid. However, 1,3-butadiene is a gas, so it's not available as a solid. So this is a gas, so we can't properly measure it. Therefore, we are going to make 1,3-butadiene within the reaction mixture, and then it will react with the malic anhydride. So that's what we're doing over here. We are using this compound called 3-sulfolene, which is a solid, so we can measure it. And once we heat it to a high temperature, the electron shifts will cause this to break down into 1,3-butadiene and sulfur dioxide. So we measured, in the experiment, we measure 3-sulfolene and we measure malic anhydride. We can't measure 1,3-butadiene because it's a gas, so we are going this roundabout way to produce 1,3-butadiene in the mixture, and then it will react with the malic anhydride. Now, all of these reactions are performed in this solvent called xylene, which you haven't seen before in our class. We were used to have diethyl ether, dichloromethane, those kind of organic solvents, but those have a very low boiling point, so they're not suitable for this reaction because we need to achieve high temperatures to allow these reactions to actually occur. So that's why we are using this specific solvent, xylene, which has a high boiling point. So we know for sure that it's not going to evaporate while we perform this experiment. Now here is our setup for the experiment. We are going to have a 3 ml vial to which we will measure 3-sulfolene, malic anhydride, and add the solvent xylene. And then we are going to fix a condenser to it. And the purpose of the condenser is to cool the system. Cold water comes in through the bottom outlet and absorb any heat that is present here, and if there were any evaporated gas molecules around here, the heat will be absorbed and they will turn into condensates, droplets, and they will fall back to the reaction mixture. And um, this type of performing a reaction, we call it refluxing, and it's a way to maintain the reactant volume during a longer period of time when we have to perform it at a higher temperature, like in this reaction, and we want to allow like 20-30 minutes for this reaction to occur in order to see some product formation. That is why we are using refluxing to maintain the reagents, prevent it from drying up, evaporating, and also we are able to mix these reactants as well through this refluxing process because they convert into gas, form droplets, fall back, so it's also providing mixing as well. Now we have a drying tube here which is filled with some calcium chloride, and these are two cotton plugs. This is not actually necessary, and we didn't use this when we did this experiment in the lab this Tuesday, so you don't have to worry about that, but you will see this in the experiment video. That's why I added that, so you guys don't get confused. And we're going to set up a thermometer on the side to observe whether we are achieving this high temperature that is required for this reaction to occur. Now, once we allow it to reflux for about 20 minutes, we are going to dismantle this and let this solution cool down to room temperature, and we're going to transfer all of it into this piece of glassware that we call a Craig tube. Now all the contents from the 3 ml vial are transferred into the Craig tube, and at this point it's a crude product mixture because crude product mixture at this point because there might be some contaminants, that impurities that come from the solvent, maybe remaining reagents, and like that. So we are going to use recrystallization in order to purify our product. That is what we will follow in the next slide. We are going to use hexane as the recrystallization solvent. So remember, in recrystallization, choosing the correct solvent is important, and the property that is important is that particular compound should be sparingly soluble in that solvent at room temperature, but should be highly soluble when we heat the solvent to a higher temperature. So it so happens hexane is an appropriate solvent to be used for the recrystallization of our product, which is cis-4-cyclohexene 1,2-dicarboxylic anhydride. In the experiment video, you will see that he's going to use some toluene as well, but we know hexane and toluene are both equally nonpolar solvents, so they are basically having the same effect. So don't get confused. I actually updated the lab manual and removed the place where it says add toluene and changed it to hexane because that's what we did in the lab on Tuesday. Now when we add hexane to that crude mixture at room temperature, we are going to see some white precipitates forming, so that would be our cis-4 cyclohexene 1,2-dicarboxylic anhydride. Now it's precipitated, and now we're going to place that tube in a hot water bath, and when we heat the solvent, this compound dissolves in hexane, so it's going to dissolve, and if there are impurities trapped within those solid particles, they are going to be released to the solution. Once everything is dissolved, we are going to take it out and allow it to slowly cool down. And with slow cooling, we allow selective crystallization to happen, so our product molecule can form interactions with other product molecules and form a very nice crystal and eliminate the impurities. So we will see crystal formation, and in the Tuesday lab we used vacuum filtration to collect these crystals. In the experiment video, he's going to use centrifugation as the method to isolate these crystals. Either way, it's doing the same thing, so don't get confused. Centrifugation can isolate the crystals, and vacuum filtration can isolate the crystals. So either method works for us. Now, for the first time in this class, we are going to discuss about theoretical yield and percent yield. So previously, you will remember in distillation and gas chromatography lab, we calculated percent compositions by measuring the area under the peaks from the gas chromatogram, and we did that again in the previous lab to see how much bromobutane we were able to form versus how much 1-butanol was left over. Now those were percent compositions relative to each other. We can also determine something called the theoretical yield. This is how much of the product can you obtain as a weight. So theoretical yield is usually given calculated as a weight. So it's basically, if this reaction works 100%, theoretically we should be able to get this much product. So basically that's the point, and we can use that as a reference point to see how successful or not our reaction was. The theoretical yield is determined by multiplying the number of product moles that we theoretically expect by the molecular weight of the product. Always remember the yield is the product, so always we use the molecular weight of the product. Now let's look at this, our main reaction, the Diels-Alder reaction. So 1,3-butadiene reacts with malic anhydride and we get our cyclic compound. And you can see the stoichiometry between them is 1 to 1 to 1. So that means basically, let me quickly switch to the pen. Basically, if we react 1 mole of 1,3-butadiene with 1 mole of malic anhydride, theoretically we can expect 1 mole of the cyclic compound as the product. And this ratio, we call it the molar ratio between each reactants and products. So the molar ratio in this reaction is 1 to 1 to 1. So we measured malic anhydride and let's say we measured 0.098 grams, and we can calculate the number of moles by dividing that from its molecular weight. And it was around 1 millimole. So that's how much of malic anhydride we measured for the experiment. Now we couldn't measure 1,3-butadiene again, remember, because it was a gas. Instead, what we measured is 3-sulfolane. Now let's assume we measured 0.260 grams of 3-sulfolane. If we calculate the number of moles for that, divide 260 by its molecular weight, and it comes to around 2.2 millimoles. Now, how much 1,3-butadiene we can theoretically have in the mixture directly depends on the amount of 3-sulfolane that we measured. So now we're going to look at the molar ratios between them. And you can see if 1,3-sulfolane breaks down, we get 1,3-butadiene. So if we have one of these, we can theoretically expect one of these. So if we reacted 2.2 millimoles, we can theoretically expect 2.2 millimoles of 1,3-butadiene to form. Now this is our main reaction, and we look at the molar ratio. It's 1 to 1 to 1. So in this case, the limiting reagent is going to be the reagent who had the lower amount. And in this case, that's going to be malic anhydride, because it has only 1 millimole, and even though there's 2.2 millimoles of 1,3-butadiene, only 1 millimole is going to react with the 1 millimole here. So malic anhydride is the limiting factor in this reaction. So in this example, malic anhydride was the limiting reagent. And we determine the number of theoretical moles of the product based on the limiting reagent. We look at the molar ratio between product and the limiting reagent. It was 1 to 1, so if it was 1 millimole of this that reacted, we should theoretically expect 1 millimole of the product to form. So now we can use this number to calculate the theoretical yield. So this was 1 millimole, and the molecular weight of the product is 152.15 grams per mole, and we're gonna get 152.15 milligrams as our theoretical yield. The percent yield is going to be based on how much we actually got in the experiment. Let's say from the experiment you got an actual yield of 50 milligrams of this product. The percent yield is going to be the 50 milligrams, so actual yield over the theoretical yield times 100. So this is approximately about 1/3 of the number we were expecting, so it's going to be like something like that. So now we can get an idea how successful or otherwise our reaction was. And you can get these kind of calculations in the exam. So make sure you practice calculating these values and make sure you're aware of how to determine the limiting reagent. Now this slide is an extra slide just for your information to show that the molar ratio is not always going to be 1:1. Okay, so the molar ratio is going to depend on the stoichiometry. Now this is a reaction that you will see in OChem 2 labs when we do the Grignard reaction, and you can see that the stoichiometry is 2, 1, and 1 product. So the molar ratio between them is 2:1:1. So finding the limiting reagent is not going to be as straightforward like a 1:1 molar ratio reaction because it's 2:1. But it's really simple because what it means is if you only had 1 millimole of methyl benzoate, this reagent, you need twice as much of this other reagent in order to fully react, right? And let's say this reagent only had 1.5 millimoles. If you just look at the numbers, it looks like 1.5 millimoles is greater than 1 millimole, so you might be tricked to think that this methyl benzoate is the limiting reagent, but actually it is not, because for this 1 millimole to fully react, we need twice as much of that from the other reagent, which should be 2 millimoles, but we don't have 2 millimoles. It turned out we only had 1.5 millimoles. So in that case, actually, this reagent will be the limiting reagent. And it's going to be that reagent that we're going to use in order to determine how much product molecules we're going to get. And you can see the molar ratio between this reagent, the limiting reagent, and the product is 2:1. So if we had 1.5 millimoles of this, theoretically we should get half that amount for the product molecule, theoretically. Something like that. And then to get the theoretical yield, you will multiply that number by the molecular weight of this product. So this is just an example to show you if you ever get like a different reaction in your exam, don't get thrown off. Take your time and look at the stoichiometry. That will help you understand the molar ratios between these reagents and products. Then you can find the limiting reagent, and that helps you determine how many product molecules you will get.